Okay, let's get started. So we're going to, okay, let's get started. So today we're going to talk about a continuation of the kernel graphic models, the non-parametric graphic models. And we're going to actually introduce another technique that will be useful for handling graphic models called kernel graphic models. So just a little bit review of what we had last time. So non-parametric graphic model, in fact, we haven't seen any true graphic model yet from last lecture, but at least we learned a few things. We know now how to embed a complex distributions like this, into a reproducing kernel Hilbert space, and also to do a number of manipulations on that, right? And also we know how to embed a conditional distribution, of C given A, for example, in a similar way. So let's review that technique a little bit, okay? So the first one is to, and of course, clarify some notation to establish, in a matrix algebraic view of the probabilistic inference and the representation problem. So here is our probability in the abstract form. And in the rest of this lecture, I'm going to use the calligraphic character P to indicate a vector or matrix or tensor view of all these entities. Okay, so this P of X is no longer a symbolic function, but it is actually a long, vector of, you can call it a discrete probability, but if it is continuous, you can imagine this is an infinite vector, something like that, right? And here is a matrix of X given Y, and that's another marginal distribution of Y. We're going to stick to this notation. And the utility of this notation is that we can hopefully use it as a proxy to establish correspondence of what we do here in the parametric space to what we do in the Hilbert space, where things become operators. Okay. All right, so what kind of operators we learned so far? So we know at least a few ways now to embed distributions into a Hilbert space. And the first one we learned is called a min map. Min map is not necessarily just say describing the whole function with its mean. That's actually not the purpose. It is really a function which is used to represent the whole distribution, right? And the form is like this. It is equivalent to taking an expectation of the feature map of the feature functions, in the Hilbert space over the distribution of X in the original distribution. Okay, so this is basically, you can imagine, somewhere in the middle. And each of these phi function are what? Are feature maps. Basically, you have points in here, and they got realized into mapped into a function in here, which is infinite dimensional. Okay. And another operator we talked about is this so-called cross covariance operator. Yeah.
I just want to make sure that I understand
something.
So there's nothing to stop us from using a kernel that's defined on multiple dimensions, right? And then using the mean embedding to have a distribution over multiple dimensions here, right?
This is a subtle topic. I actually intentionally brushed away. So here it is a single variable. You have, there is nothing stopping you from calling this a single variable a multidimensional thing as long as you don't care about the interdependencies within it. You just have a vector. Then you can blindly call it a mapping over there. But just for clarity here, I want to use it as a single dimension. If I have two dimension, what we used to do in this graphic model is that if you have two variables, it is a graphic model with explicit dependencies. Therefore, it takes some other structure. If you really don't care about structure, like you have multivariate distribution, you want to use a table, a full table, or you use a full density function, then you can roughly establish that. But for that, you don't gain a lot. Okay. your goal is to use the graphical model, and here I provide the basic building block on every particular random variable. And you can imagine that it makes sense now, right? So I have the singleton, okay, now mapped into a Hilbert space as a function. Then I basically mapped this guy. This is not a singleton anymore. It is the a distribution of a pair of random variables. Then the way I map it is to use an operator, okay? And there are actually, the operator basically is to transform a function into another function, if you remember, right? And that's basically corresponding to our operation over two random variables. If so, remember this with operator. Now you can basically do this, right? Right, and you also can have this. The operator C operates on F, or gets you to a function like this. Okay, that basically says that through operation, you can turn a function into another function, which is roughly equivalent to turn a distribution into another distribution. And in the probabilistic model, in the matrix form, you also probably see that if I have a x, and the way I want to transform into a y, is probably to put down x given y, and multiply that and go through here. So basically, this is a function that an operator that turn function from one space to the other space. And the way to define this operator here is a outer product between the two feature maps, okay, and then take an expectation over the joint distribution. And this is roughly a graphical picture of that operation. You have an outer product of this two Hilbert space, and then here you take the mean of all these different projections. Okay, so this way we actually embed a joint distribution of two random variables. And then the third operator we learned is that of a autocovariance operator, which is the outer product between the mean map, between the feature map itself, right? And what's this used for? This is roughly a proxy to a diagonalized marginal distribution of a single random variable. Okay, and but be a little bit more careful that here this is just a embedding of this. The actual form is actually a outer product between two feature functions, which roughly correspond to the autocorrelation x squared. Okay, so in this case, the embedding is not to embed x itself, to embed this one. And then you can use these two operator to in a compound way to have what we call a conditional embedding operator, which gives you a operation on functions that is similar to what a conditional distribution would do. For example, this operator has the following property. If it is evaluated on y, meaning that y is actually taking now a particular value, then what it translates to is that this particular conditional distribution is a distribution over x over a single random variable, because y is already fixed. And therefore, by definition, in the Hilbert space, it is defining an expectation over the transformed x, given y is fixed. Therefore, this must be a function rather than operator, right? And then how can we use this conditional embedding to realize that? Basically, now you have this conditional operator, and then you are going to multiply that with this feature function over the y, okay? And this operator over a function turns this whole thing into another function, which is now the conditional distribution of x, okay, evaluated at y already. Okay, this is just a single variate distribution. And so what is the effective consequence of this? So if you want to use a matrix kind of intuition to visualize this, this is like a very high-dimensional matrix, right? It is kind of a matrix where each entry is a x given a particular y, something like that, right? So, and then this one on the left-hand side is actually a vector, right? It's a vector that is describing the conditional probability of only a single random variable x when y is fixed in some places. So what that translates to is roughly corresponding to taking suppose that in this table corresponding to the C, we have this dimension to be y and this dimension to be x, then this entity roughly corresponds to a particular slice in that matrix, right? We need to take a slice out of the matrix. And by placing this operator on top of the function, you turn this function into another function. That's roughly translating to turning this matrix into a slice out of it. So this operation is called slicing operation. Okay, you slice a conditional probability table, okay, and get a particular distribution out of it. And in the matrix operation case for discrete probability, it corresponds to this operation. If we set this y into a discrete value, then you are going to now multiply this matrix with a delta function to suppress all the other columns but one, which correspond to this particular thing. Okay. Again, it is a little bit difficult to directly draw the equivalence because here, to make it a tabular representation, y needs to be discrete and x needs to be discrete, right? And in here, there is no such assumption. Therefore, you should imagine in the space of an infinite vector. And this one, is no longer a delta function. It is just, a feature map that is going to be used to take a slice out of it. One thing that is a little bit counterintuitive, which is a little bit also difficult to me, is that usually, when we multiply, a matrix with a vector, it is not about taking a slice out of it. It is almost like a marginalization, right? You are collapsing a vector on top of a matrix. Therefore, sounds like adding together all these matrix into that. Right? But here it is not the case. It is indeed to take just a slice out of it, okay? Because this is not really a matrix multiplication. It is an operation of a function by an operator. Okay? But symbolically, you can view this as that. So to take, for example, a marginal step, a marginalization step out of it, we actually have other operators down the road. So slicing creates this kind of effect. Depending on different values of y, you will be getting different columns, okay, out of that joint distribution table. And here, therefore, you have all these different realizations of the probability of x conditioning on a different context. And they are also different from a marginal probability of f. But the symbolic similarity between this, among these three is that they are all just a function, okay, in the Hilbert space. Therefore, you can imagine that they take these different forms. This marginal is here, and this conditional is in here, and that conditional is here. They are all distributions in the same Hilbert space, okay? And therefore, my phi function in here and here is basically a feature function that used to slice this operator in a different fashion and taking different columns from this infinite matrix. So that's the intuition I want you to build. So why we like Hilbert space embedding in the first place? I think we have a number of arguments already, right? We can represent a discrete distribution, a non-parametric distribution in a richer fashion. But operationally, does it give us any, at least, if not advantage, but at least it creates no more trouble? That's actually something we want to care about. For example, in graphical models, some of the very common rules we are going to use are these two rules that actually form the basis of decomposing a bigger graphical model into pieces, right? So that you can recover, the joint distribution by manipulating on small building blocks. And the first rule is called the sum rule, which, lets you basically get a marginal distribution, over a multivariate distribution by implicitly summing over some random variables you don't care about. And this is a generic form where you integrate out the variables that you don't care about. But on the other hand, if and also you can break this joint distribution into this one, and then what you do is you sum over all the variables of y, right? And if y is a discrete, then that leads to basically a p of x and y matrix times this vector. And we claim that this same rule can be realized in the Hilbert space using this operator, which is kind of unintuitive, but symbolically they give you the same idea. Basically, there are some representations of the marginal of y now by a mean map. This is the mu y. Recall this is called the mean map of a single univariate distribution. And then this is a conditional distribution operator, which corresponds to this one. And then once you multiply this operator over that map function, you get another map function on x. So this symbolically creates the same sum rule here. Okay, and the benefit of this is that now in here you can play the kernel trick to actually play with a lot richer distributional family than you can do here. Here, if you put p here, you must be living in a parametric space with a lot of assumptions on the form of the distribution. But in here, there is nothing like that. And chain rule is another important rule we must honor in whatever space you want to represent a distribution. So in the original context, we have the chain rule defined as just a product between these two, and without summing over the x. But in the Hilbert space, we actually now are representing this using these compounded operators. The first one is a conditional operator like this, and the second one, py, strangely is now replaced by this autocovariance operator. So if you remember, why is that? Why now the same y, py here and here had two different representations? One is the mean map, the other is the autocovariance operator. Well, we will know the why later, but at least now you want to remember, indeed, depending on whether you sum or not sum, you are going to need two operators to represent the y. Okay, this one, remember, is a diagonal matrix, okay, of something like that. And once it is multiplied with other matrix, it avoids a summation of the argument of interest, right? It will keep everything the same. And that's basically what the chain rule is about. Chain rule is not about marginalization. It is just about decomposition of multivariate distribution into smaller pieces. Okay, and there are some subtleties in terms of why here you have a mean map which seems to be operating on just the phi itself, and here you're operating on the outer product of two phis. And there are some subtle differences which we will see later on. Because in here, this is after all just an operator. If you want to use the operator to get the number out of it, you need to actually apply it to a function. Sometimes that function will be used to cancel out these operators. Anyway, these are complex things we will learn later. And we will start by proving some of these rules and then see how they can be used. And that's basically the main topic of today's lecture. So let's take a closer look of the sum rules. Again, there are different sum rules, right? One is this summation, as by definition over a two-variate distribution. And the other, and unfortunately, this operation cannot be realized, okay, in a Hilbert space, because that operator isn't defined. In the Hilbert space, all we have is a feature map, and therefore it doesn't really tells you how exactly that particular argument can be manipulated. This y, for example. The second way is to use this sum rule. Okay, this is defined as a product, a inner product between a matrix and a vector. And because it is an inner product, in the linear algebraic definition, they already implicitly suggest a summation step when you create that. Right. So we are going to actually use this to inspire the Hilbert operation that we talk about. All right, so the way we're going to establish this connection between the linear algebraic operation and the operation in the reproducing kernel Hilbert space is to hopefully form a direct kind of mapping of the matrix here to the operators in those space. And we already explained how roughly each of these entities correspond to operators or functions in the Hilbert space. So let's take a look. So this is the sum rule we want to honor in our Hilbert space. And again, here is the explicit matrix algebraic expression of the sum rule. This is the matrix of all the numbers involved in the conditional probability distribution table. And this is the marginal of y in the form of a finite vector. Okay? And here are just examples of that. Remember, this is not the joint probabilistic table. Okay? This is a conditional probability table in which a column actually can be self-normalizable. Okay? These two sum to 1. And they correspond to the conditional probability of x given a fixed value of y. And now we have 2 of that. And here are the marginal of the y's. All right. So the equivalent view, okay, in here, again, using the linear matrix algebra, this is the chain rule, by the way. So chain rule is different from that in the sense that even though it is still the product between 2 matrices, the end outcome is a joint distribution of 2 variables, right? So in here, you can see the operation here look symbolically the same, okay? But this summation over y is gone, it's not there, okay? They're not going to marginalize. Therefore, this operation, even though they look like this, cannot be look like this one, cannot be directly used because here implicitly there is a summation. Therefore, we need to now drag this y vector into a diagonal vector, a diagonal matrix, and then once you multiply, you will have this full table preserved. Okay. All right. So now these are the 2 rules we need to now realize in the RKHS space. And so here is what we are going to do. By the way, this is just the chain rule, for 3 random variables expressed in a matrix algebraic rule. And remember, here I'm already using the graphical model assumption where we assume that B and C are conditionally independent given the A. Otherwise, you will need to have a bigger matrix where, for example, this one, if this assumption isn't true, then what you have must contain something like this, which is leading to a bigger table. And that's exactly why graphic model help us if we have a structure between the random variables. So this is a longer chain rule. And how, for example, can we perform an operation like this with, here this example is rich in the sense that it contains both a sum step and also a joint step. We are going to integrate out the A, but we need to keep both B and C in the table. So how can we actually realize this operation in the Hilbert space? So now let's have a proof first of the chain of the sum rule. Remember, the sum rule is that P of x equals to P of x given y dot P of y. And we want to now replace that with mu of x equals to C of x given y and the mu of y. Okay, so that's basically a operator we need to establish. So we start from here. P of x, okay, basically can be explicitly expressed by taking expectation on something called an indicator vector. Okay, imagine x is discrete. Then here I have two indicator vectors indicating the two values of x. Okay. And then, a conditional distribution of the x given the y, is basically, a expectation also on that indicator, but using a conditional distribution. Okay, so this is the basic definition of these two distributions. And in this case, which is the random variable? Which is the invariant tables? So basically, this delta x is the random variable, right? Or you can call x is the random variable as well. But this guy is not the random variable, right? This guy is just the parameters in that distribution, and this guy is not the random variable either. And you can also take this guy to be maybe a vector, and this is a matrix. And the operation of inference is to take the right column or rows from that matrix of vectors. All right. Okay, so now let's see what's going to happen in the Hilbert space. We say that this one corresponds to a min map. So we're going to now take this down, replace that with the mu x. Okay. And then in here, we're going to replace the indicator vector with our feature map of that particular random variable. Okay. And again, this mu is a function that we're going to obtain, and this is a random function. Okay. Depending on your value of x, it will be projected into different places, and then you are going to take an expectation on these random functions. And the proof of the correctness of chain rule in the matrix form is very, very straightforward. Just now bringing our definition of px given y and py. So we wrote down here, and here the p of y is now expressed as expectation over the indicator vectors of y. And I have a few steps going on. So for example, in here, I'm going to take the y out because what? Because this p of, there are some notational confusion here. This p of x and y is actually not a random variable, even though the y appears here, makes you probably take it as a random variable. But what I really want to use here is that this guy is a table of all these numbers. Okay, I'm going to basically use this to pick out the right column from that table. So this is actually a bunch of numbers which are constant. And then if you take expectation, you can basically move this out of that. Okay, so these two gets combined. And then the next step is to now basically define this. Okay, so now you are going to pick a y out of this table, right? Using this delta function. Okay, and this whole thing is not becoming a random variable because depending on the value of the y, you can pick different columns from this p table. Okay, so I'm now going to rewrite it. Suppose you pick that out already, then you are going to have a conditional distribution of x given y, and then it will be operating on that indicator function of the x. Okay, so this step is a little bit subtle. I hope you get it. And then once you have here, you can now merge these two expectations using the fundamental property, of a conditional distribution or conditional expectation, and therefore you are now effectively taking expectation on the feature vector, with respect to this joint distribution of x and y, and then at the end of the day, you have a p of x. Okay, so that's basically the proof of a matrix sum rule. Okay, which is now making explicit that the sum operation can happen, in this matrix manipulation if we assume that the y is and the y and x are represented by indicator functions. Okay. And why we need this? This is kind of not very interesting because we know sum rule just by original definition already. We don't even need to usually think about how to prove it's correct, right? So I expose the correctness of this in this proof because I want to now replace everything with what we used to have in the Hilbert space. So in Hilbert space, each one of these entity had a counterpart, right? For example, the delta function is what? Correspond to what? A feature map, right? Basically, we say that in the Hilbert space, we no longer have the original data point. We basically have a random, feature map from that data. So we're going to now actually replace, the delta with the feature function, and replace the delta x with its own feature function as well. And we replace the conditional probability table with the conditional operator like this. And then we ask whether this is equal to this or not. Okay. So this coming from here to here is by definition, because mu y, the mean map, is by definition equal to the expectation of the random feature map over y. Okay. And then the same kind of justification we went over carried here as well. We're going to take the expectation of over x given y out, because yes, this expectation over y out, because this is not a random variable. This is just a feature, a operator. And you now take it out, and then you have the conditional operator directly working on a feature map. And by definition, this corresponds to this one, right? Taking the expectation over the feature map of x under this conditional distribution of x given y, and then having the y value being conditioned on as a slicer. So this is the definition, and of conditional embedding. And then again, using the property of expectation, these two expectations get merged together, and they are going to be operating on just the phi x function itself. And then this is giving you the definition of the mean map of x. Okay. So now we have a quick proof of the sum rule in the RKHS. And so why it's interesting? It is going to be very interesting if you are going to combine them with the chain rule as well to do probabilistic inference in the kernel space. So here is an example. Suppose we have now a graphical model of these 4 nodes, and we are going to now replace these CPTs, the conditional probabilistic tables, in the graphic model with the RKHS operators or functions. Okay, then everything we do in the original graphic model now can be lifted into the Hilbert space and taking place in a non-parametric fashion. And what we gain from there is that when you define CPT or define a parametric form of conditional distribution of B given A or C given B, they are all needing strong assumptions, right? Whether they are discrete distributions or they are Gaussian distribution, all these assumptions can be very, very restrictive. But with the RKHS operators and the functions, you virtually don't make any assumption. The only assumption you made is the feature map. Okay, the feature map has a variety of different things, and even with a simple choice such as the RBF kernel, you already are operating in the infinite dimensional space. And from our experience in HSVM, we know that it's going to capture a lot of subtleties in the original distribution. Right. So let's first do it symbolically, and then let's see how algebraically and mathematically they are correct and they can be manipulated. They can be managed. So say let's ask a simple marginal inference problem. Out of this 4 variable distribution, I want to compute the marginal distribution of the first node and the last node. I'm going to integrate out everything in the middle. Okay, that's a pretty standard inference problem in graphical model. And in the discrete case, right, and we actually know how to do it in the linear algebraic way, without a kernel embedding, if we are willing to take on simple assumptions like these are tabular distributions. And then what's happening, hopefully, you can see it is like this. The smarter way of doing that is, this is a table of conditional. These are tables, and then here is this. These are basically our, Bayesian network chain rule. The thing it takes to define the Bayesian network are all here, right? Marginal of the root and the conditional of all the children given their parents and all that. And then to do inference, if a smart guy would probably realize that, you all need to do is to actually, here I want to point out an accident. So if you do it in a naive way, like you have this matrix, and you do multiplication, okay, all the way to here, you actually can, get some actually nice effects. For example, here is a table of B given C, a D given C, and here is a table of C given B, for example. And if you multiply this together, what do you get? You multiply these two matrices, what you get is what? It's still a matrix, right? And here there are 3 random variables, but after you multiply, you get a matrix, which suggests that it is an entity of 2 variables. What is that? It's B and D. C somehow gets marginalized, right? And then you keep doing this, and you actually are really performing elimination or marginalization, and then your B and C are gone. But if you are uncareful and you do it all the way to here, and then here you have a vector of A, and you still do this inner product between the matrix and the vector, what you get is actually a vector. And the A is gone, even though your original inference problem wants you to compute the joint between A and B. Right? So that's basically telling you why sometimes we need to have just a mechanical device that is a little bit more convenient. We define the first one not as a vector. We define that as a diagonalized matrix, and then using again the chain, the sequential multiplication of matrix, you actually will get a joint of 2 things. Okay, so that's just a easy kind of operation, and this is going to give you the table of joint distribution between A and D. Okay, your goal is to compute the probability of A little equal to little a and D equal to little d, and how that can happen. Just think in an algebraic way. This guy corresponds to maybe a element in the matrix. How to take that out using a algebraic operation. Use 2 delta functions, right? Right multiply a delta function and the left multiply a delta function. Then you pick the right row and right column. You get it, exactly. So that's what we're going to do, and you basically, pick this out. All right. So this is basically what's going to happen purely mechanically in the, in the matrix and vector domain. Okay, for discrete distribution. Now I ask, can we actually lift the same thing to a Hilbert space? To not a simple Hilbert, but a reproducing kernel space. Okay, we prove that chain rule is correct, also in the reproducing kernel Hilbert space. We also know the correspondence between the entities in our matrix world to the Hilbert space world, right? Such as a conditional correspond to an operator, and variables correspond to singleton marginals correspond to a min map, and the variable indicators correspond to what? A feature map, a random features, right? So we're going to basically do this replacement. Everything here now is no longer defined as a conditional probability table. It is defined by an operator. Okay, we're going to talk later what these operators are. They actually, representing themselves can be another challenge, but let's imagine we have that symbolically. Then we're going to have all these operators, and the first one is now a autocovariance matrix rather than the min map, because we want to get avoid being marginalized out accidentally, right? And the sum product on this graphic model, in fact with kernels, is going to take place like this, right? So for the first 2, if you want to generate a joint, you just apply the sum product rule and then get this operation. And if you want to have the whole thing, you just did exactly what I had before for the matrix manipulation. You just multiply these 4 operators together, okay? And without a proof, in fact, it might be interesting for you to go home and do a proof by yourself. You can show yourself that this actually leads you to an operator. This is again an operator that gives you the joint distribution of embedding of the joint distribution of these 2 random variables. Okay. This itself is a auto cross covariance operator of A and D, which are not adjacent in the graphical model, but through all this sequential, product operation between multiple operators, you achieve the effect of marginalize out the variables you don't care about. Okay. All right, and then again, getting the numbers out, getting the actual density of the 2 specific numbers. You are going to left and the right inner product, inner multiply, this feature map with the operators we just obtained. Okay, clear about that? So all these are very symbolic. And then let's maybe get a little bit more real on what these numbers are. So now we get this and that, what these numbers are. Okay. In the previous linear algebraic space, we basically get, through this operation, we get basically a number picked out. That number corresponds to exactly the probability of a pair of numbers, right? And in this space, what is that? We are having really a continuous distribution, not even with a parametric form. Then what that particular entry is, because every number should have a 0 probability in a continuous distribution, right? Under a conditional density function, right? So let's actually take a look at that. In the simplest case, here we are basically using the operator with this inner product of two feature functions. Okay, and this is an embedding of 2 random variables, 2 random variable distribution. Let's take a simpler look. How about taking a look of the embedding of a univariate distribution and then let it apply on a particular feature function. So what is this? We are now basically evaluate the min map at a point. Okay. Remember the reproducing rule, right? So here, when any function, inner product with a feature, it's basically evaluating that function on that feature point, right? So we are now evaluating the mu on this particular data point. So what does that lead you to? Just expand the definition of a min map. It's equal to the expectation over phi x, okay, which is a random mapping function. And this is the same mapping function, but fixed at x bar. Okay. And this is an inner product between the 2 feature function. And both of these are infinite dimensional vectors, right? But their inner product is well defined in the Hilbert space. It is the kernel function, right? So we're going to use this kernel. And this is a kernel of your choice. Say, let's choose the RBF kernel in here. Then what you get is basically this guy. Okay, when you are evaluating the min map on a particular data point, you get this particular thing. So what is this? If you can recall. Maybe I should give you even a more symbolic form. So if anybody remember what is a kernel density estimator, right? A kernel density estimator basically tells you that if you want to estimate the density of a particular data point under a unknown distribution represented only by data, you are going to use this rule basically, which is corresponding to sum of these kernels defined each on data points. Okay, In fact, the way I write this slide should be the opposite. I should show you this. This is what people are familiar with, but this translates to analytically an expectation over the kernel function. Okay. And this guy actually exactly corresponds to this in here. Okay. So what does that mean? It means that if you are evaluating the min map on a particular point, it actually gives you the kernel density estimator of that point. Yes?
Well, there is a subtle difference because with KDE, you're going to be shrinking the bandwidth as your number of points increases.
Mm-hmm.
Here we're kind of keeping like a fixed bandwidth.
Even in KDE, do you really shrink? You actually keep it as a fix, right?
You would want to shrink it with the number of points in the example.
Well, that's because you choose a different data set. I'm saying, given your data set, you're going to stay with one bandwidth, right? So here the same thing. It's basically, go with the data. And if you go with a different data set, you say, I chose a different kernel, right? So in a sense, within the same problem, you don't, redefine the. Of course, you could. That actually translates to a more complicated feature map, but the form is actually the same, right? All right. So that basically gives you, a nice kind of glimpse about the utility of the RHS operators and also their way of representing complex distribution. You basically can use linear algebraic operations, in the Hilbert space to do inference in your original distribution without assuming a parametric form. And in this case, this is an inference of evaluating the probability of a point, right? And previously, we have inferences on marginalizing unnecessary random variables and keep the rest. And once you keep the rest, that basically gives you a new operator only working on the random variables of interest. And then when you are evaluating this operator on feature maps, you again get a density estimator of that particular form. Here you have the density estimator of A and D jointly, but without, again, making subtle assumptions on the distribution of the multivariate problem. Okay, so now we are going to talk about the multiple random variables. And here you actually see a stronger kind of incentive of why what we just talked about become particularly useful. So in a multivariate density problem, say you have O parameters, okay, what do you do even with kernel density function? You can argue that what I show here isn't buying you too much because, even without using the kernel mapping, I can still figure out, using the kernel density function like this, right? And but this is just for one-dimensional X. If I have an O-dimensional X, multivariate distribution, what do you do in kernel density estimator? Well, you choose a kernel and then compute this somehow something like a distance function in that high-dimensional space, right? Suppose we choose the same kernel like this. And in this Gaussian RBF kernel, you are going to now equivalent to evaluating this in the product of O such one-dimensional kernel function. And if this O is very high-dimensional, you are going to get a pretty bad estimation, right? Because somehow you are running into the curse of dimensionality in this case, right? A lot of small numbers gets multiplied together, right? And this is like also evaluating this very huge covariance operator of not only two but many variables, and by definition that correspond to a feature map of multiple infinite dimensional the outer product of multiple infinite dimensional feature functions. So if you resort to your kind of geometric imagination, this one can be translated into a tensor in a very, very high-dimensional matrix, right? And in principle, you can also define or estimate this tensor just by computing all this, sample mean of the outer product of features. But you can imagine it's going to be a very poor estimator because the tensor is so big, and your data may be so actually few. Therefore, many of the estimator can be very unstable. So this is actually what people don't want to do, and that roughly translates to the following concept. In when we talk about high-dimensional multivariate distribution in the discrete space, we kind of say that we don't want to have this giant table, documenting the discrete probability of all combinations of multiple random variables, because that table is too big. What we really want is to use the Bayesian network intuition to break this big table down into smaller pieces. And each piece is a local conditional distribution of some random variable given others, right? So we don't actually know how to do that in the kernel density estimator, but we actually know that how to do that in the reproducing kernel Hilbert space. So we're going to show you how to do that. So the problem, as I just repeat, is that this estimator will be rather inaccurate. And what we want to do is to now break this very high-dimensional operator, tensor operator, into hopefully a sequence of these low-dimensional bivariate operators. And this roughly corresponds to the following translation. You translate a naive tabular graphical model, or tabular multivariate distribution, into a graphic model multivariate distribution where you have a factorization rule to factorize the huge joint into smaller factors. And in this case, what you saw before as this big operator, tensor operator, is corresponding to the big table in your discrete distribution. And what we want to do is to use the kernel graph model technique to break them into smaller pieces. And each of the bivariate or maybe low-dimensional operator will be also subject to kernel manipulations. Okay. All right, so let's take a look of this even simpler model with only 3 random variables. Okay, and the pieces that we need due to this graphic model inspiration are basically proper representation of the local conditional distributions. And we have 2 of them plus a marginal. And we know the kernel embedding of that. Okay. And now we can show you that how can we actually estimate these different kernels. Okay. So again, up to now, I've been doing only symbolic justification. I say that this huge kernel, this huge imaginary operator of A and B and C can be now broken into these 3 pieces. But I never talked to you about exactly what this thing look like, right? We know the definition of that. If you still remember, what's the definition of this? Let's in the simplest case. What is the definition of the autocovariance operator? It is the expectation of the outer product actually no, this, right? And then we kind of wave of hand and say, okay, this definition, we can do it. But the question is, can we do it? This phi is an infinite dimensional vector, right? And as I can show you later, in here, the definition of our autocovariance actually leads you to this. And what is this? What is this phi? It is an infinite dimensional vector. And therefore, this one is actually the outer product of 2 infinite dimensional matrix. Okay, did you realize that? So this one is basically a matrix like this. And here I have 1 to up to n data points, and 1 to up to n data points. But along this dimension, we actually have infinity. Okay, we never say that explicitly, but implicitly as the case if we choose the RBF kernel. Therefore, there actually isn't a concrete or explicit kind of representation of this on machine. You have it represented on your paper like this, but it's not on machine. Okay. So what is representable? That's something we need to ask. So what is representable is basically this feature, this kernel matrix. We know very well about that. What is a kernel matrix? Well, it is the inner product, right, between 2 feature maps, right? So we have in every entry, a inner product between the 2 random features, and we have n by n matrix like this. So this is pretty manageable, but not this one. right? And that's because this one is an infinite matrix. So now we need to basically step back and see how actually we can find a way not to directly manipulate with the operators, the conditional operators or other operators, because even though they are symbolically very nice, but on my computer I couldn't put it anywhere, right? So let's study some properties of this. So conceptually, how can we, turn them into some equivalent entities that is of finite dimensional, and then using these entities, we can still achieve the same thing, to be achieved by those infinite entities. Okay, that's actually something we need to study here. Okay, so here are some potential operations you may want to do with this infinite dimensional matrix. You can view this as our design matrix in the infinite dimensional feature space. So one is the linear combination. Okay, so this phi, can be right multiplied with a finite dimensional vector. Okay, this is a vector over the n data points, and you get a linear combination. Okay, so in a sense, you are getting a function, in Rn to another function in Rn. Okay, so in this case, turning a function to another function suggests that this phi of x can be treated as an operator, right? Because these are basically, infinite dimensional, matrix. And another thing that you can operate on is this one, right? So here I'm now having a function, not a vector anymore, okay? And this function itself is a reproducing function, is a function in the reproducing kernel's Hilbert space. Therefore, it is infinite dimensional, but it is reproducing. And then what can we do on that is it can be left multiplied with the transpose of this phi matrix, which is called the adjoint, right? And that gets us to what? To an n-dimensional vector, okay? Okay, so let me just repeat. So here you are transforming this function into a infinite dimensional space. Okay, so this is an infinite dimensional function. And here you are doing the reverse. So here you have a function in the R infinity, or maybe we call it the Hilbert space. And after this transformation, due to adjoint of phi, you get into a V, maybe not V, but something, okay, in this Rn space, right? So these are basically the forward and backward operation that can be induced by this phi operator. Okay. And so empirically, how this can be estimated is basically due to this definition on outer product between two infinite dimensional matrix. And what we want to do is to ask, can we actually avoid directly playing with these operators, even if they give us the nice chain rule and operations on the kernel graphic models, but we can use something equivalent in the finite dimensional space. So the only thing we have in the finite dimensional space, okay, is this kernel matrix that we originally have, right? Which is not the outer product, but the inner product between these two feature maps. Okay, and is there a nice connection between this K and this C, so that we can hopefully, whenever we see a C, we can turn them into something that is computable from K. Okay, so that's a question that I can imagine important. So here is the intuition. So why you can even believe that some operations on C can be replaced by some equivalent operations on K? Well, here you need to ask about the amount of information that is contained in this K matrix and in C matrix. So if you see how C is computed, it is due to the inner product between these two feature vectors. And you are doing that on n data points, right? So these are infinite-dimensional vectors, and therefore you get an infinite-dimensional matrix. But this infinite-dimensional matrix is actually computed from n data points. What's the rank of that matrix? It is rank n. And you actually don't need to use anything bigger than rank n to represent the information there. That's the intuition, right? And this guy is exactly rank n because it is computed from a n by n dimensional matrix, assuming that the data themselves are not redundant, okay? And now we are trying to establish a deterministic equivalencies or a relationship between this and that, so that you can see the nice connection. All right, so now we ask when actually are these conditional operators or the joint embeddings actually work to perform the inference problem. So we know that by definition the conditional operator is actually defined by the product of two operators. One is the joint embedding operator and the autocovariance operator. And this one, by the way, is a inversion of autocovariance matrix. And if you are familiar with linear algebraic operation, you know that whenever we do an inverse in a high-dimensional space, to make sure they are invertible, we usually add a little residue to make them full rank. Because at the very beginning, this one, we already knew that it is not full rank. It is rank n, but the whole matrix can be very big. But even if you have an unknown number of data points, you want to make sure that at least there is this device here to make them full rank. And again, this I matrix here is how big? In this case, it is infinite dimensional, right? It is still a very big thing. So only symbolically this can happen, but in reality you don't have this. But now we are going to use, a number of lectures ago, remember we actually learned a matrix inversion lemma, in which we established a number of identities between the matrix inversions. This is one of the matrix inversion, right? So without showing you the proof, there is this very useful matrix inversion identity which actually tells you, how to actually manipulate the ordering matrix of different ranks can be manipulated. And without showing the proof, after adapting what you had before into this identity, you actually get a alternative definition of the covariance of the conditional operator, which is like this. Okay, so if you look at this, it is still for sure infinite dimensional, right? But now it looks like the actual computation may not need to happen in an infinite dimensional space, right? Because what you have is this calculation you have to do. This is a n by n kernel matrix, if you realize that. This actually corresponds to this, right? And again, I have the regularizer, but this regularizer is actually in the n-dimensional space, okay? And then this whole thing is also a n by n matrix, okay? So just to stare at this a little bit more, this is a n by n matrix. This is an intermediate entity to produce the conditional operator. And here, to produce the same conditional operator, you have to deal with this inversion, which is in the infinite dimensional space. Okay, even though they are equivalent, but this one gets a n-dimensional operation. And then you create the whole thing back into infinite dimensional because here you have the feature maps, which is a flat thing that is on the one direction infinite, on the other direction n-dimensional. All right, so now we can now rewrite the building blocks for the original graphic model, the CAA, CBA, and the C given A, into these redefined matrices. Or you can call it also operators because these are really the operators, right? So what do you see? Well, let's see how actually they can be used. Okay. So when you actually do the chain rule, we already showed that this guy actually corresponds to the product of these three operators. And plug in the earlier definition of these three operators, we have this long, this actually what turns people away from doing kernel graphical models because it looks really, really ugly, right? It's not as clean as this one. But it gives you some advantages in terms of the computational manageability. So if you look at all these components, okay, this whole thing is for sure infinite dimensional, still infinite dimensional. Okay, but to actually build this operator, you actually don't need to always stay in the infinite dimensional space. For example, in here, you see this. This is a kernel, okay, and it's defined over the inner product of the A maps. Okay, and this is by definition n-dimensional because you have just n data points. And this one is another kernel defined on the B maps. Okay, and the things gets blown up when you actually apply this to the operator, which turn a finite function into an infinite function. Okay, and then you can, and actually even in here, you can still say, okay, do I need to keep this? Because even if I, can handle all this intermediate stuff, I'm still going back to the infinite dimensional space because of these operators. But the truth is that this is not something you actually need to keep, right? You basically, the philosophy in here is that you're not going to cook the whole dish for tomorrow, and tomorrow you'll sit there and pick 2 dishes out of it and eat and save the rest. What you do is that you prepare the raw material and not putting them into the dishes, which can be infinite dimensional. Basically, you are having materials for all possible dishes, but tomorrow, if you want to eat 2 of them, I'm going to pick those things out and only cook that 2. Okay, that's what's happening here. So when you are doing the inference, after all, you care about the density or the probability of specific realizations, say A equals to little a and the big C equals to little c. And then you need to do another operation on these feature maps, right? So imagine this is an operator, and they operate, this is a operator on function and also on another function. It gets you a real number. So at the end of the day, this infinite dimension in here is going to be gone because it will be left multiplied with another infinite dimensional vector. Okay. So with that, now you can see what you actually need to keep, in your database or in your probabilistic knowledge base for inference. You need to keep this, okay, which enables this operation. That's a kernel function in the n by n dimensional space. And this guy is another kernel function, okay, on the C maps. So at the end of the day, what you really, really need to worry about is not the list of these operators, which are symbolically very clean, but operationally all defined by a sample mean over infinite vectors. Okay, this is symbolically clean, but operationally not possible. What you actually do is to keep all these intermediate entities. So you are representing a distribution, using this guy, which are, you can call it pre-probabilistic distributions or pre-distributional representations, which are all finite dimensional. So this dA is a matrix, okay, defined on the kernel over A, and the B and the T. Actually, why I call it T or C, because this is, if you see the chain rule, of a multivariate graphical model, A, B, C, and D, and maybe even more. Each of these intermediate conditional distribution kernel or conditional distribution operator will correspond to one of these a term like this. But the last one, okay, which is a terminal kind of a conditional operator, actually correspond to a very strange kernel matrix without taking any argument from the C. Okay, so I call it T. But everything in the middle actually has a form like this that you can hopefully enumerate, instantiate. And then evidence is also expressed in the term of a kernel function. Okay. So all these are finite, and the intuition here is really they are not directly what we did in our graphical model where we write P of A and P of B given A and P of C given B and so on. That's basically what we do in the graphical model. And then we make this translation to here to make the operator looks like what we did in graphical model. But computationally, in the reproducing kernel Hilbert space, you don't actually keep all this direct embedding of the original distribution because these embedding are infinite dimensional. You keep something that is derived from the embedding, okay, in here, which we could call the raw materials for the dishes. And when you actually want to get the inference done, you are going to pick the right entry from here and recover the probabilistic number you want to have. Okay, so that's the only thing I found to be a little bit counterintuitive. But if you get used to that, you probably can feel more comfortable in this kind of operation. All right. Yes. Mm-hmm.
If you could go back to the previous slide.
Okay.
So in parametric models, you can evaluate points. I mean, you make assumptions, but then you can evaluate your function on points that you have not seen in your data before. In this case, what would be the equivalent? Can you do it?
You can evaluate functions.
For example, I mean, you want to do inference in your graphical model, and you want to evaluate the probability of one of the variables taking on a certain value that you have not seen in your data before.
You don't have this A and the B are not. Remember our kernel density function. These are basically the new. Every unseen data point can also translate to a random feature in the map, right? And you just use that to pick, because this is actually very good for your problem. With unseen data, that going to get evaluated, using these kernel functions. These are not SIM data. Remember, the SIM data actually entered here. Okay, these kernels are computed from the training data.
So what's the notation?
This one.
Kernel AA1 to n.
This one.
Basically, you're selecting all the.
I'm keeping a placeholder. This is basically a function now. These are actually the function. Okay, if you have a kernel which is not completed yet, basically you will have. You can imagine a kernel with one additional row and column that correspond to your data point. When we say unseen data, it is a convenient English, but you actually see it because you evaluate already. It's there. That becomes your data. Okay, then you are going to use this to compute its probability or its density. So the data is there. You don't prepare anything for data that is not there yet. Okay, and that's actually the differences, because in the density function, in the Gaussian form, you seem to have a function and you plug in your new data points. Same thing here, you plug in your whole thing into the matrix, into this kernel matrix, right? Because in the kernel matrix, remember, RBF kernel, is expressed as xi and xj. Now you basically turn them into a feature map of xi, and this xj is some argument that you want to plug in, and that's where you plug in the little c and a. Okay. Again, so this takes some digestion, and I want you to read the paper more carefully and get a sense out of it. Here's another insight. Maybe I should just spend less time on this. Kernel sometimes is, understood as a way to compute pairwise affinity and stuff like that. But another way is to view them as a non-parametric evaluation of points. So all these kernel functions can be actually expressed as a evaluation, of a particular point, okay, on all the other training points in the data set, right? And that basically gets you, a non-parametric notion for any kind of a plug-in data. You are going to be able to evaluate on the existing data sets, in the training data. So here you can imagine. What is the model? You can probably ask, what do I learn? What is the, we're talking about only inference algorithm. We're not talking about any learning algorithm in here. So do we learn anything here? In the probabilistic notion, what is the learning task we have accomplished so far? That actually gets you to a very deep question of why you don't see the word learning a lot in the statistic literature. in statistics literature, you only see the word inference. There isn't a word about learning. Okay, and I believe it has something to do with here. In the non-parametric statistics, there's nothing to learn. Okay, your knowledge is the data, and the model is defined directly on data already. You are not supposed to put a parametric assumption on that. So there are no parameters for you to learn. Okay, so what you actually have is a database or a knowledge base of a kernel evaluated or anchored on your training data point, and they sits there to wait to plug in, your testing data, just like what you do in k-nearest neighbor. Okay, your k-nearest neighbor are the data set. It is your model, and when you want to evaluate, you plug in your new data and compute the distances, and that's exactly what's happening in here. Okay, I think I'm all there, and here I have a use case for the type of technique I just used, and it's very natural. So here's a problem of protein configuration estimation, and you can imagine, the way to describe a protein configuration. Protein, of course, is a collection of all these molecules, oriented in different way, right? And they are connected, through this backbone polypeptide chains. So this backbone can be considered as the edges in the graphic model that connects all the little nodes. The nodes correspond to every atom or every molecule. Then at the end of the day, the way to define an energy state is to figure out collectively the joint kind of position or orientation of every molecule. And the orientation in this case can be described by maybe the spherical coordinates, with their two different angles. Okay. And my goal is not to tell you protein chemistry or stuff like that. My goal is to tell you there are problems where the states are defined by continuous numbers and they don't follow Gaussian. Actually, people don't know what their distributions are. So all they know is that I have data with all these real numbers. Okay. And then it is natural now to define a graphic model like this. These are the graphic model. The graph structure is what? Is the backbone on the protein, which tells you what molecule connects to what. But it don't tell you how the molecule is oriented in that chain. Then what you do is to now figure out, define a state for every random variable, in this case a 2-value state, and with continuous number. And then what you need to do to define this graphic model, instead of assuming maybe, all right, let's maybe put a here, and then B of B given A is a Gaussian. You don't do that. Okay, you start to really ask, can we define a kernel function between these two things in a purely non-parametric fashion? Okay, and that's basically what enables you to model the whole energy configuration in a flexible way. And what we learned so far gives you now a formal procedure of tying together all these kernels to write down the joint distribution of the entire graphic model using the chain rule or the sum rules. Okay. All right. So that's the second lecture on graphic model. I actually have a number of slides later on to tell you a even more weird case that involves propagations on trees. Maybe if you allow me, let me take 2 minutes just to give you the insight about this. So far we've been talking about a chain. And therefore, all we need to deal with is an operator of 2 variables, right? And that can be basically defined by a bivariate operator. A tree is strange because it has 2 children, right? And therefore, you need to now define something like C of x and y given z. Okay, and just imagine here we are actually relating this to a table, to a matrix, and here we have to do that with a tensor. Okay, so the material in here tells you how to actually build the analogy on operations on tensor algebra to do the inference. So I leave that for your own reading during the weekend. Next week, I'm not going to talk about tensor algebra. I'm going to talk about spectrum inference, in which I have this large kernel matrix, which can be also still expensive. You have a lot of data. But what if many of the data points are just redundant or very somehow not necessarily telling you different information. And we're going to use a spectrum approach to reduce the rank of those matrices even further to do low rank approximation and inference. And again, that's another benefit from graphical model or from kernel graphical model, because in the original graphical model, you don't even have the leverage of playing with tensor and playing with the matrix decomposition. And now we have that. And we're going to show you a use case in natural language processing called parsing. So hopefully we conclude that part of the lecture nicely. All right, any questions? If not, we'll see you next week.